Here in section 3.2, we're going to talk about compound interest. And compound interest is when you invest your principal and you earn interest on that principal for a certain length of time, and then at the end of that time, at the end of that period, the interest then, along with the original principal, gets reinvested at exactly the same rate. Then you get to earn interest on the interest. All right, so let's look at an example to see what do we mean by earning interest on the interest. So let's say that you deposit $1,000 in a bank and it's going to pay 8% compounded quarterly. When you see the word compounded in the problem, then you know you're talking about compound interest. Remember that quarterly means 4 times a year. How much would the bank owe you at the end of 1 year? Okay, so we have 4 different quarters, and each one of those quarters is what we would call a period. And the interest gets calculated for each period. Okay, so we want to calculate how much money that we would have in the bank after the first quarter. Okay, so I'm going to use our formula that we talked about. We have our principal plus the interest, and we're going to calculate it for each quarter separately. So for the moment, we're using that simple interest formula. All right, so how much will we have at the end of the first quarter? Okay, since we're talking about 1 quarter at a time, what length of time is that? So 1 quarter. So remember that 1 quarter is 1/4 of a year. So remember our t-value has to be in terms of years. All right, so how much do we have at the end of the first quarter? The original principal is $1,000. So we'll set P equal to 1,000. Our interest rate, we said, was 8%. So as a decimal, that's 0.08 times the length of time, which is 1/4. Okay, put all of that into our calculator, and I get $1,020 for that first quarter. Now here's what happens as we go into the second quarter. As we go into the second quarter, the money that we bring in as the principal is actually going to be the original principal and the interest that we earned during the first quarter. So the $20 that we earned during that first quarter now becomes part of the principal for the next quarter. So we have $1,020 plus $1,020. So the P is now including that interest, and we still have the same interest rate like we said, and we're doing 1 more quarter, so another 1/4 of a year. We'll put that into our calculator, round to the nearest 2 decimal places. So now at the end of the second quarter, we have $1,040 and about 40 cents. Okay, now for the third quarter, we're going to do the same thing. The amount that was sitting in the bank at the end of the second quarter now becomes the new principal. So now the investment for that third quarter is the $1,040.40. So now we get to earn interest not only on the original principal, but now on the interest, that $40.40 that we've accumulated. Okay, so our R value is still the same. Our T value is 1/4. Put all of that into our calculator. We'll round to the nearest 2 decimal places, to the nearest cent. And so I have $1,061.21 approximately, rounding to the nearest 2 decimal places. All right, so what happens at the end of the fourth quarter? Okay, so what's going in as the principal now is what was sitting in the bank at the end of the third quarter. So now the P value for that fourth quarter, $1,061.21. At the interest rate of 8%, again for 1 more quarter. So 1 more period. Okay, we put all of that into our calculator, and I get about $1,082.43. So at the end of that first year, after those 4 compounding periods, or after those 4 quarters, this is the amount of money that will be sitting in the bank. So this is what we call compound interest, when you get to earn interest on the interest that was earned in the last period. Okay, let's compare this to simple interest. Okay, let's compare this to simple interest. What happens with simple interest that doesn't happen with compound interest? Okay, so when we're talking about simple interest, we only get to earn interest on the original principal. So that means you do not get to reinvest the interest that you earned from the previous quarter. So how much do we have after the first quarter? So I'm going to calculate our interest. Remember, our interest equals PRT. So how much interest do we have at the end of the first quarter? I'll have 1,000 times our R value, which we're going to use still 8%, and our length of time is still 1/4, still that 1/4. Put all that into the calculator, and I get $20. So I get $20 of interest after the first quarter. So I end up with $1,020 sitting in the bank at the end of the first quarter. Now, here's where things get different. When I go to calculate the interest for the second quarter, I do not get to calculate the interest on the $20. I have to go back to the original principal. So if I do that calculation, I'm going to get $20 again. So that means I get to add $20 to what was sitting in the bank before. So that's just $1,040. So each quarter I get to add just straight $20 because that's going to be the amount of interest every time that I get to calculate on that original principal of $1,000. Okay, so at the end of the fourth quarter, we have $1,080 sitting in the bank if we only apply simple interest. So when we compare the end amount for compound interest and for simple interest, the amount for compound interest is going to be larger because you get to reinvest and earn interest on the previous interest. So it may not seem like a lot right now, it's only about $2.43, but we're only talking about 1 year. Over time, the difference would be more and more. So when I look at this graph, the blue graph here is compound interest, and the red graph here is simple interest. The horizontal axis represents time in years, and the vertical axis is representing the money. If we look at about $7,000, how long would it take us to earn $7,000 with compound interest and simple interest? So with compound interest, it looks like that would take just a little bit over 20 years. But to earn $7,000 using a simple interest account, it looks like it would take almost 80 years, a little bit less than 80 years. So about 25, let's say about 75 years. So you can see that you will earn a lot more money a lot quicker if you talk about compound interest as opposed to simple interest over time. Okay, so let's look at our compound interest formula. What we did up here when we talked about compound interest is we calculated compound interest for every quarter individually. We don't want to have to do that. There is a formula that will take us from beginning to the very end of the account for several quarters, for several years, all at one time. Okay, so we call this the compound interest formula. We have A, that represents the future amount, is equal to the principal times, parentheses, 1 plus the interest rate, which once again is going to be represented as a decimal and not a percentage. We have M. M is going to represent the number of compounding periods per year. So if we go back up here, in this example, the M value would be 4 because we calculated interest 4 times during that year. There would be 4 compounding periods per year. So in this example, our M value would be 4. Okay, and then we have T. T represents time in years. So in the compound interest formula, we actually have an exponent. This is what we call exponential growth. So that blue graph there is growing very quickly. We call that exponential growth. And that exponential growth comes from the fact that we have an exponent in our formula. So let's use this formula to do the calculation that we did for compound interest at the beginning. Okay, so I'm going to go back up to the top of the page. All right, and so to calculate the compound interest, we did 4 different calculations. So now we're going to be able to do just one. So we're going to use that compound interest formula. A is equal to P plus R divided by M to the M times T power. Okay, so our original principal was $1,000 plus the R value, which is that interest rate written as a decimal. divided by m. M is the number of times the interest is compounded per year. So we're talking about quarters. We did that 4 times a year. In this example, our m value is 4. So our exponent would be 4 times how many years? Well, our t value is 1 because we only did that for 1 year. So we're going to put that into our calculator. Just simplify a little bit before I do that. You don't have to do a lot of simplification, but I might write 4 times 1 as just 4. Now let's put that into Desmos and see what our final answer is. Okay, so I have 1,000. Put my parentheses. That's 1 plus 0.08 divided by 4. Come outside of that parentheses, and we're going to use the a to the b power to give an exponent. What I would recommend that you do is, if you have anything in the exponent, go ahead and just put parentheses around the exponent. It makes things a little bit easier and a little cleaner. And so we get $1,082.43 if we round to the nearest 2 decimal places. So that actually did all of those calculations for us and got to that final answer at the end of the year for the amount that would be in the account using compound interest. Okay, so we can see the benefit of having a compound interest formula. Instead of doing these 4 calculations for each period, we can just do 1 calculation for the entire length of the account and get the same exact answer. Alright, so let's look at example 1. Let's say that you deposit $1,000 in a bank for 5 years. Okay, so the $1,000 is going to represent that principal P, and the 5 years is going to represent the time. So our T value is 5 years. How much would the bank owe you at the end of 5 years for these different types of compoundings? So we're going to look at 4 different types of compoundings. We have 8% compounded quarterly, 8% compounded annually, 8% compounded semi-annually, and then 8% compounded monthly. All right, so we want to look at how much the bank owes at the end for these different types of compoundings. Okay, so our formula is A is equal to, we have P times 1 plus R divided by M to the MT power. Okay, so we want to figure out how much the bank owes us at the end. So we'll plug in our P value of 1,000. We'll have 1 plus our R. Our interest rate is 8%, written as a decimal, divided by M. Now, what is the M value? When we do compounded quarterly, how many times a year is that? So quarterly means we have 1, 2, 3, 4 different quarters. So that's 4 times a year. So when you see compounded quarterly in a problem, your M value is going to be 4. So it's going to be compounded 4 times a year. So our M value is 4. So I'll put 4 up in the exponent times the T value, which for this example is 5. Alright, we're going to take this and we're going to put it right into our calculator in Desmos. Alright, so I'm here in Desmos. I'm going to type in 1,000. I'm going to type my parentheses, then we're going to do 1 plus our 0.08. You don't need the leading 0. You can if you want. Divided by, make sure when you do the division that it's only dividing the interest rate, so that 0.08 divided by 4. Come outside of those parentheses, and then we're going to raise this to the power of 4 times 5. So a to the power of b to get up in that exponent. I recommend that you put parentheses to capture everything that's up in the exponent. And I'm not going to simplify this time. I'm just going to write 4 times 5 up in the exponent. So that gives me $1,485 and how many cents? I'm going to round to the nearest 2 decimal places. Alright, so here's the answer that Desmos gave me. We always want to round to the nearest cent, which means the nearest 2 decimal places. So we round to the nearest cent because we're talking about money. Okay, so we want to keep 2 numbers after the decimal place. To round to the nearest cent, or to the nearest 2 decimal places, you're going to circle the third number that comes after the decimal. Okay, if this number is between 0 and 4, then the number in front of it is going to stay the same. If this third number that's circled is in between 5 and 9, then it's going to round the number in front of it up. Okay, so that actually is in between 5 and 9, so it's going to round the 4 up to a 5. So our final answer will be $1,485.95. Okay. So our next part is asking us to do compounded annually. Annually means one time per year. So our M value is going to be 1. So we're going to do A equals our $1,000 for our principal times 1 plus our interest rate, which is still 8%, divided by 1, and then our M value 1 times the T value of 5, because we're talking about 5 years. Okay, we're going to put that into decimals and then see what we get. Alright, so I have this for my last calculation. I'm just going to change the 4 to be a 1. And everything else is going to stay the same. So I get, let's see, $1,469, 32, and then I have an 8. So I'm going to round to the nearest 2 decimal places, or to the nearest cent. So the 8 is going to round that 2 up to be a 3. So $1,469.33. Alright, the next part says compounded semi-annually. When we're talking about semi-annually, we're talking about twice a year. So we have 2 halves of the year. So semi-annually means that you are compounding twice a year. So M equals 2 when you see semi-annually. So to calculate this, we're going to do A equals our principal 1,000 times 1 plus our interest rate 0.08 divided by our M value, which is 2. And then up in the exponent, we're going to do M times T, so that's 2 times our T value, which is 5 years. All right, so now we're going to put that into decimals and see what we get. Okay, now I've already typed all of this in again, so I'm just going to switch out the 1 for a 2. All right, I get $1,480.24. The third number after the decimal is in between 0 and 4, so it's going to keep the number in front of it the same. So $1,480.24. Alright, so the last part says 8% compounded monthly. So monthly means M equals 12. So it's going to compound that interest 12 times per year. So we're going to do A equals the principal of 1,000, 1 plus our interest rate, 0.08, this time divided by 12, because our M value is 12, and then up in the exponent we're going to do 12 times 5. 5 being the T value, 5 years. Alright, once again we're going to put that into decimals and see what we get. Alright, so I have this already from the last part. I'm just going to change the 2 to be a 12. Alright, so our answer is $1,489, and then I have 0.845. So the third number after the decimal is a 5. If that number is 5, between 5 and 9, it's going to round the number in front of it up. So that's going to be 0.85. When you see those different types of compoundings, make sure you know what your M value is. All right, for example 2, it says, what amount will an account have after 2 years if $5,000 is invested at an annual rate of 6.8%? And we have 2 different parts to this problem. Part A says, what if it's compounded daily? Part B says, what if it's compounded continuously? So let's look at part A first. We see the word compounded, so we know we're going to use our compound interest formula. So our compound interest formula is A equals P times parentheses 1 plus R divided by M to the M times T power. Okay, so the P value is the $5,000, that's our principal. The T value is going to be 2 years. Our interest rate, we have 6.8%, so that's going to be moving the decimal place 2 spaces to the left. So that's 0.068. So we're going to do A equals 5,000 times 1 plus our interest rate divided by m. Now what is the m here? This says compounded daily. So we want to know how many times per year do we compound if we're compounding every day. When you see daily, we're going to do 365. So 365 days a year is what we're going to use for section 3.2. So when you see compounded daily, your m value is 365. So we're going to do 365 times our t value, which we said was 2. Okay, we're just going to put that into decimals and see what we get. All right, so I'm going to type in the 5,000 parentheses. I'm going to do the 1 plus the 0.068. Make sure you divide just that 0.068 divided by the 365. Come outside of the parentheses and then hit your exponent button. And I recommend that you go ahead and put parentheses there and let the calculator do that multiplication of the exponents for us. 365 times 2. Okay, so our answer is 5,728 and we have 336, so we're going to look at the 6, the third number after the decimal, and we're going to see, does that round that second number after the decimal up or keep us the same? Since it's a 6, it's going to round the number in front of it up to be a 4. So $5,728.34. Alright, so that's how much is in the bank if we compound daily. What if we compound continuously? Okay, so this one's a little different. When you see the word continuously, okay, we're going to use a special formula called the continuous compound interest formula. Alright, so the only time that you're going to use this formula is when you see two words in a problem, compounded and the word continuously. Alright, so the formula for that is A equals P, and that's being multiplied times e to the RT power. Okay, where P is the principal, E is that number that we talked about in one of the first review videos. It's about 2.72 approximately. We're just going to type it into our calculator and let our calculator keep track of that. And R is our interest rate, and T, once again, is measured in years. So if it's compounded continuously, we're going to use A equals PRT. Okay, so our A equals, our P value is 5,000. We're going to multiply that times E. E stays E, and then we're going to raise it to the power of R, which in this case is our 0.068, times T, which in this case is 2. Okay, we're going to type that into decimals. Alright, so I'm going to type in the 5,000. I'm going to go to the ABC. I'm going to type in a letter. I want the letter E. Okay, and I want to raise that to an exponent, so I'm going to go back to my numbers. Alright, and I'm going to hit a to the power of b, so that puts me in the exponent. I'm going to go ahead and put parentheses to represent that exponent, and I'm going to let my calculator do the multiplication for me. 0.068 times 2. Okay, so I get about $5,728.41 when I round to the nearest cent or to the nearest 2 decimal places. Okay, so we see that continuous compounding gave us a little bit more money in the end than compounding daily. Compounding continuously means you're compounding an unlimited number of times, so basically more than 365 times for that year. For example 3, we have that if an investment company pays 3% compounded semi-annually, how much should you deposit now to have $10,000 5 years from now? So one of the key words we see in this problem is the word compounded. Okay, that means we're going to use our compound interest formula. So we're going to use A equals P times 1 plus R divided by M to the M times T power. It says semi-annually, so that gives me an M value of 2. So that means the interest will be calculated twice a year. Our interest rate, we have 3%. So we know that's going to be 0.03. And we have two numbers down here. We have 10,000 and we have 5 years from now. So that tells me I have a t value of 5. So we have the R value, we have the M value, we have the T value. So the question is that 10,000 the A value or the P value? So when we look at the problem, it says how much should you deposit now? So that's the present value, how much I should deposit now to have $10,000 5 years from now. So this means that this is a future value. This is how much I want to have in the future. So that is my A value. So our A value is 10,000. Our P value is what we're solving for. So the P value, the principal, how much we should deposit now is what we don't know. So let's plug in all of our values and see what we get. So I have 10,000 on the left-hand side of the equation in place of A equals P. Since I don't know the principal, since we don't know that P value, I'm going to leave it just as P. So we're going to do parentheses 1 plus my interest rate, which is our 0.03. We're going to divide it by M, which we said was 2, and we raise that to the 2 times T power, so the M times T. 2 times T, T is 5 years. Alright, so let's simplify a little bit here. Two times 5, I'm going to go ahead and just write that as 10. So our goal is to solve for P. We want to get P by itself on one side. Okay, so how can we get P alone? Well, P is being multiplied times all of these numbers, times this entire group. So to get P by itself, I'm going to divide by everything that's being multiplied times P. So I'm going to divide both sides by the group. 1 plus 0.03 divided by 2 raised to the power of 10. So that's my value of P. Now I'm going to plug that into Desmos and see what that value actually gives us. Okay, so that's 10,000 divided by, I'm going to put my parentheses there, that's 1 plus 0.03, divide that by 2. We're going to come outside of the parentheses, make sure you stay at the bottom, hit the exponent button, and then I'm just going to put one number up there, I'm just going to put 10. So I get $8,616.67. Alright, so this is how much we would have to invest now, so that 5 years from now we would have $10,000 sitting in this account that earns 3% interest if it's compounded semi-annually. Example 4. If an investment company pays 2.5% compounded continuously, how much should you deposit now to have $25,000 36 months from now? So I see a few keywords. I see compounded. So I know I'm going to use some kind of compound interest formula, but with that I see the word continuously, which means I'm going to use that special formula, the A equals P times E to the RT power. Okay, so when you see the word continuously, this is the compound interest formula that we use. So we need to know what is A, what is P, what is R, and what is T. So let's go for the interest rate, 2.5%. So we know that's going to be move the decimal place 2 spaces to the left. So that's 0.025 written as a decimal. Okay, what about 36 months from now? Remember that we want our T value to be measured in years. So when we see the unit of months, we're going to take the months value that we're given in the problem and we're going to divide by the number of months that are in a year, which is 12. 36 divided by 12. If you want to, you can simplify that, and that would be 3 years. Okay, so the last part is the 25,000 the A value or the P value? So the question says, how much should you deposit now? The amount that you deposit now is the P value. That's the principal. The 25,000 is a future value. So that's what we want to have in the future. So that tells me the A value is 25,000 and the P value is what we don't know. That's what we want to solve for. So let's plug everything into our formula. 25,000 on the left side of the equal sign equals P. We don't know what P is, so I'm going to leave that as just a capital P, times E. Remember, in this formula, E stays E. We're going to raise that to the power of R times the T value, which is 3. Now our goal is to solve for P. We want to get P by itself on one side. To get P alone, well, it's being multiplied times all of this. So we're going to divide by all of this. And we have to do that on both sides. So our P value, after those things cancel out, will be $25,000 divided by E to that exponent. So we're going to put that into decimals and see what we get. Okay, so I get 25,000 divided by, go to my letters, hit E, go back to the numbers, and I want to make sure that this is the exponent for E. Put our parentheses to represent that exponent. And I'm going to put 0.025 times 3 in that exponent. So our p-value turns out to be $23,193.59 when I round to the nearest 2 decimal places or to the nearest cent. Okay, so $23,193.59 is the amount that we would have to deposit now to have $25,000 sitting in the bank 36 months from now at 2.5% compounded continuously. Example 5. How long will it take $3,000 to grow to $10,000 if it is invested at 9.6% compounded monthly? So I see that word compounded. So we're going to use our compound interest formula. So we have A equals P times 1 plus R divided by M to the M times T power. So in order to use this formula, there are some things that we want to know. What is A? What is P? What is R? What is M? And what is T? Okay, so compounded monthly. So monthly means that we have an M value of 12. That's 12 compoundings per year. 9.6%, that's our interest rate. We're going to write that as a decimal. Move my decimal place 2 spaces to the left, so that's 0.096. All right, so we have $3,000. And it's going to grow to $10,000. So this is how much I'm investing now. That's the principal to get a future value of $10,000. So that's our A value. So we know the A value is 10,000 and the P value we know is 3,000. So the question is how long? So we don't know how many years that it will take for $3,000 to grow to $10,000. So in this case we're solving for T. So let's plug everything into our equation. Okay, then we're going to raise that to the 12 times T power. We don't know what T is, so I'm going to leave T as T. Now when we go to solve this equation, this is an exponential equation. The reason why I know it's an exponential equation is because the variable is in the exponent. Okay, so this is a problem that we saw in the section 2.6 review. So if you need to go back and look at the 2.6 review video to solve exponential equations, then you're welcome to do that. But if we want to solve for a variable that's trapped in the exponent, then the first step is to isolate the base. So what is that exponent actually applying to? So the exponent applies to everything that's in front of it. So in this case, it applies to everything in the parentheses. So 12t is the exponent, The thing right in front of it in the parentheses is what we call the base. So our first step for solving an exponential equation, we said, was to isolate the base. So we want the base and its exponent by itself on one side. So that means the 3,000 is not part of the base, it's not part of the exponent. It's being multiplied times the base, so I'm going to get rid of it by dividing both sides by 3,000. So 3,000 on the right hand side is going to cancel out, and I'm left with 1 plus 0.096 divided by 12 to the 12t power. You're welcome to simplify 10,000 divided by 3,000, or you don't have to. You can leave it as 10,000 divided by 3,000, and the calculator will do a lot of that work for us. Alright, so after you've isolated the base, the second step is to apply the natural log to both sides. So I'm going to apply natural log to the left side, and then I'm going to apply natural log to the right side. Okay, the third step is to use the power rule. And we talked about all of this in that 2.6 video to bring exponent to the front of the natural log. So what that means is that once we apply the natural log, we're allowed to use log properties. So the exponent that's on all of that base is actually going to be multiplied out front of that log. So I'm going to take the 12t and I'm going to multiply it out front of the ln. So on the left side I have natural log of 10,000 divided by 3,000 equals, now on the right side I have 12 times t times that natural log of all of that. So the exponent goes away and is now multiplied outside of the log out front of it. So our ultimate goal here is to solve for t. We want to get t by itself on one side. So the last step is to solve for the variable. Okay, if I want to get t by itself, right now I have 12 times t, so I can get rid of the 12 by dividing by 12, so the 12s will cancel. And I also want to get rid of all of this in the natural log, so I'm also going to divide by the natural log of all of that. So this and this cancel, and I'm left with just t by itself on the right hand side. Now if I divide by 12 and the natural log of all of that on one side, I have to do exactly the same thing to the other side. So this right here is what I'm going to type into my calculator for that t value. Okay, so let's type that into Desmos and see what we get. Alright, so I'm here in Desmos. I'm going to go to Functions, and I'm going to find that natural log. So it's under Miscellaneous. We're going to find ln. And I'm going to type into the top part there, I'm going to type in 10,000 divided by 3,000. Okay, so that's at the top of that fraction. I'm going to come outside of the parentheses, and probably the best thing to do in this case is to go ahead and highlight everything at the top of this fraction. So I want all of this to divide by everything I'm about to type in the denominator. So we want to make sure that fraction bar goes underneath the ln and also the parentheses. So now I'm going to type in 12 and then natural log again, and then the 1 plus the 0.096 divided by 12. Okay, so it says our t value is 12.5914 and so on. So let's round to the nearest one decimal place. Okay, so this is the answer that we got from Desmos. So I'm going to highlight kind of what I want to keep. I want to keep one number after the decimal place. In order to round to the nearest one decimal place, I will look to the number that's in the second position after the decimal, and I would decide, does that round the number in front up or keep it the same? And since this is 5 or larger, it's going to round the number in front of it up. So that would be 12.6 approximately. Now 12.6 what? Remember we were solving for t. T is always measured in years when it goes into the formula and also measured in years when it comes out of the formula. So we have 12.6 years is our value for t. Okay, so when we go back, 12.6 years was the number of time that it was going to take $3,000 to grow to $10,000 under these conditions. Example 6. In a suburb, housing costs have been increasing at 3.2% per year, compounded annually, for the past 4 years. A house worth $260,000 now would have had what value 4 years ago? Alright, so looking at this problem, I see the word compounded, and it says compounded annually. So I know I'm going to use the compound interest formula. A equals P times 1 plus R divided by M to the M times T power. And there are certain values of these variables that we want to know. So let's see what we know and what we don't. Okay, so an easy one to pick out would be 3.2%. That's my interest rate or my rate. So let's convert that to a decimal. So that's 0.032. Okay, so it says compounded annually. Annually means I'm compounding 1 time per year. So that's an M value of 1. And it says that this has been going on for the past 4 years, and we want to know what value the house had 4 years ago. So that looks like a t value of 4 years. So the only thing we want to know is what is the a value and what's the p value and which one are we solving for. Okay, so we have $260,000. We want to know what value the house had 4 years ago. So which one is the later of those two? Which one is it in the future and which one's in the past? So if I have a house that's worth this much now and I want to know what happened 4 years ago, 4 years ago was in the past. So this must be a future value or a later value. So the a value is $260,000. What we want to know is what was the original cost of the house 4 years ago. So that would be the value in the past. That's what we would have started with. Okay, so $260,000 is actually the future value. Okay, so let's plug in everything into our formula, and then let's solve for the p-value that we don't know. Alright, our t-value is 4. Alright, so we want to get p by itself. Our goal is to solve for that original. Alright, so we want to get p by itself. So we want to solve for that original cost of the house. So we want to get p by itself by dividing both sides by what is being multiplied times p. So I'm going to divide both sides by everything that I see here. Alright, so that cancels out and I'm left with p. And this is what I want to type into my calculator to find that p value. Okay, so I'm going to pull up decimals and let's see what we get. Alright, so I have 260,000. I'm going to divide that by parentheses 1 plus. Now of course you can simplify these things as you go, but you do not have to. Desmos will do a lot of that simplification for you if you're not sure what you're going to get. So make sure you hit that exponent, come outside of the parentheses, hit that exponent. I'm going to go ahead and put parentheses for the exponent, and then I'm going to type in 1 times 4. Alright, so I get $229,221.08. All right, so what I found is what the cost of the house would have been 4 years ago that is now worth $260,000. Example 7. If the population in a particular country is growing at 2.1% compounded continuously, how long will it take the population to double? A couple of key words. We see compounded, so we know we're using one of our compound interest formulas, but we see compounded continuously. So when you see the word continuously, you want to be thinking about the A equals P times E to the RT power. That's the formula we use when we see the word continuously. All right, so let's write down everything that we know and what we want to solve for. All right, so the rate, that percentage, we're going to write that as a decimal. So that's 0.021. And our question is, how long will it take the population to double? How long sounds like a time. That is what I don't know. So I don't know the time. I don't know how long it will take. So we're going to say T is what we don't know. Now it looks like we also don't know A and we don't know P. So let's talk about this. How long does it take the population to double? So what does it mean for the population to double? So let's take it for instance. Let's say right now I have 2,000, and if I want that to double, I'm thinking about multiplying it by 2. So doubling means multiplying by 2. So if the population now was 2,000, in the future I would have 4,000. If the population now were 7,000, then that tells me in the future we're talking about 14,000 people. So we're not told what the current population is or what it is in the future. So really what we want to know though for the population to double is for every one person now, we want to know how long it'll take one person to become 2 people. So how long will it take the population to double is essentially asking how long will it take every one person to double to become 2 people. So in this case, it does not matter what your current population is or what your future population is exactly. We just want to know how long does it take one person to become 2. So I want to prove to you that it really doesn't matter if you use 2,000 to 4,000, 7,000 to 14,000, or from 1 to 2. It doesn't matter which one you call the future value and which one you call the present value. So I'm going to solve this problem starting out with kind of 3 different approaches. First of all, let's call the p-value 2,000, so that present value 2,000, and let's say the future value is a population of 4,000. So let's plug that into our formula. So I have 4,000 for that A value. The P value is 2,000. And we have times E to the R times T power, which T is what we don't know. Once again, this is an exponential equation. How do I know this is an exponential equation? Because I see the variable that I want to solve for is trapped in the exponent. When I'm solving an exponential equation, the first step is always to isolate the base. So what is the base for this exponent? The base for the exponent is e, and it's always only e. If you have e in your problem, the base is always e. So that means the number that's multiplied times e needs to move. So if I want to say 2,000 times this, and I want to get rid of the 2,000 that's multiplied times e, I'm going to divide both sides by 2,000. Okay, so 4,000 divided by 2,000, let's simplify that, that's just 2. 2,000 divided by 2,000 is 1. Okay, and of course we don't need the 1. I'm just going to leave it there for emphasis. Now what if you had used the 7,000 and the 14,000? So your present population, 7,000, your future population, 14,000, and let's apply the same problem. So our A value is 14,000, that's on the left side in our formula, is equal to the P value, which is 7,000, times E to the RT power. Once again, it's an exponential equation, so we want to get the base and its exponent isolated by itself on one side. So I'm going to get rid of the 7,000 by doing division. Okay, on the left-hand side, 14,000 divided by 7,000, if I simplify that, that becomes 2. 7,000 divided by 7,000 is 1, and then we're left with that e to that power. So you'll notice that after we've isolated the base, we end up with exactly the same equation to solve. Now, what if we had just used an a value of 2 and a p value of 1? What if we had just used that from the beginning? Okay, what would that have looked like? So I'm going to write that down here. So p value of 1 and then an a value of 2. Plug that into our formula. We get 2 is equal to 1 times e to the r times t power. Okay, so what we've just seen is that it doesn't matter what your original population is and what your future population is. If it doubles, all you really need to know is where we're trying to figure out is how long does it take one person to double to be 2 people. And the answer is going to be the same no matter what a value and p value that you use, because essentially when you do that first step of solving an exponential equation, all of them are going to give you exactly the same result after that first step. Okay, so it doesn't matter. You can pick which one you want. So if I want to isolate the base here, do I really need the 1 there? Well, no. 1 times that is just that, so let's just get rid of the 1. Okay, and once I've isolated the base, we said we apply natural log to both sides. Okay, and once we apply natural log to e, the natural log and e are going to cancel each other out because they're inverses directly. And so I'm left with just that exponent 0.021 times t. On the other side, I have the natural log of 2. Okay, and once again, our goal is to solve for t. We want to get t by itself. So I'm going to divide both sides by what's multiplied times t. Okay, so this is our t value. That's the exact value. Let's put it into our calculator to figure out approximately what that t value is. Okay, so in my calculator, I'm going to type natural log of 2. Make sure you highlight all of that. Hit divided by. You want that fraction line to go underneath the ln and the parentheses. And then I'm going to type in my 0.021. So it looks like we get about 33 years. So our t value, 33 years. Okay, so what that means to our original problem, we were trying to figure out how long it would take the population in this country to double. And so now we know that it would take 33 years for the population to double. All right, quick question. What if you were asked to find out how long it would take the population to triple? What would your a and p value have to be? Okay, and hopefully we proved at this point that it doesn't really matter what your a value and your p value are. What you're really asking is how long does it take one person to become 3 people? Okay, so we just need that population to triple.